Hey everyone, welcome to The Explainer. Today we're looking at a visual manual that is honestly an absolute lifesaver if you're working in the solar industry. Understanding the protocols in this guide is absolutely critical for preventing catastrophic failures in photovoltaic or PV installations. If you work with solar panels or you're just really into electrical engineering, you've got to know that what you can't see up on the roof can actually be the most dangerous part of the entire system. We're going to break down exactly how to handle these systems safely, focusing specifically on how to prevent devastating failures at the MC4 connectors.
Here's our roadmap for today. First, the real danger in PV systems. Second, the physics of the DC arc. Third, the anatomy of a PV fire. And finally, our safe operation manual. Let's get right into it.
Section 1. The real danger in PV systems. All right, get ready, because we're going to bust a really common and frankly, super dangerous myth in the electrical world.
If you came up doing classic AC installs, you were probably taught to look out for things like high current, standard overloads, and cables slowly overheating over time, right? And that totally makes sense for a residential AC outlet, where the risk builds up predictably. But man, taking that exact same mindset onto a DC solar roof, that is a fatal blind spot. In the DC world, we aren't waiting for a cable to slowly melt. We're dealing with an instantaneous, catastrophic threat, specifically the DC electrical arc.
It's a huge misconception. A lot of folks just assume overheating is the ultimate enemy here. But severe PV failures, they rarely happen because your cable cross-section is too small or from a normal overload. The real monster, the one that causes immediate, devastating damage, is that DC electrical arc.
To put this into perspective, a standard 4 to 6 square millimeter solar cable handles a 10 to 15 amp load all day long without breaking a sweat. Overheating is a completely controlled risk if you fuse and design it right. A DC arc, though, it happens instantly the second a live connection is broken. The temperature instantly spikes to over 3,000 degrees Celsius. I mean, that literally melts metal, vaporizes plastic connectors, and can set a roof on fire in a matter of seconds.
Section 2. The physics of the DC arc. So why does DC behave so aggressively compared to AC? Let's dive into the science. Check out the difference between these currents. With standard alternating current at 50 Hz, the current actually changes direction and hits zero 100 times every single second. It has this built-in zero crossing, which naturally chokes out an electrical arc. But direct current, it's a continuous fire hose, no zero crossings whatsoever. Because of that, a DC arc just does not want to die. It burns steadily and has to be forcefully interrupted.
This is exactly why using AC-rated breakers on a DC solar system is such a deadly mistake. AC breakers rely on that zero crossing to put out arcs. Try to stop a DC current with one, and the contacts will literally weld themselves together. The plastic housing just melts into a puddle, the current keeps right on flowing, and boom, you've got a sustained fire. You absolutely have to use dedicated DC-rated hardware. No exceptions. And then there's what we call the sun factor. This is crucial. You can't just flip a main switch and magically turn off the roof. As long as the sun is shining, those modules are pumping out voltage. Sure, you can isolate the inverter down below, but those cables coming off the panels, they are still an active, live voltage source. Which brings us to VOC, or open circuit voltage. Basically, this is the maximum voltage a solar module kicks out when no current is flowing. Since we obviously can't turn off the sun, our one and only safety mechanism before we ever touch those cables is to drop the current all the way down to 0 amps.
Here's the deal. A dangerous, stable DC arc needs two things to survive at the exact same time: high voltage, which the sun is constantly giving us, and sufficient current. Take away the current and the arc simply can't exist. So our primary mission before physically disconnecting anything is isolating that current down to 0.
Section 3. Anatomy of a PV fire. Okay, we know the physics now, but how do these massive fires actually spark out in the field?
Well, looking inside the actual anatomy of an MC4 connector, we see that fires don't usually start from tiny cables. They almost always start at points of high electrical resistance. We're talking bad wire crimping on the metal pin inside, defective DC switches, poor contact from mixing different brands of connectors, or the absolute worst offender, physically pulling this connector apart while it's under a live load.
If you disconnect under load, here is the terrifying chain reaction. Imagine it's a sunny day. You've got maybe 700 volts and 12 amps running through the line. The very millisecond you pull that MC4 connector apart, an arc jumps the gap. Instantly, you've got a 3,000-degree plasma fireball on your hands. The plastic melts, and a major structural fire is born. Honestly, so many PV fires start exactly this way.
So that leaves us with a huge, incredibly practical question. If the sun is always shining and pulling a connector apart creates a literal fireball, how in the world do we safely disconnect these things in the real world?
Section 4, Safe Operation Manual. Let's get into the actionable stuff. Here is your definitive protocol for isolating the circuit safely.
If you take absolutely nothing else away from this explainer, permanently burn this golden rule into your brain. The standard MC4 connector is not a load break switch, period. Unlike a massive, heavy-duty rotary DC isolation switch, your standard MC4 is just a connection point. It's not designed to interrupt current, and it absolutely cannot extinguish a DC arc. Never, ever treat it like a switch.
So how do we do it right? There's a strict 4-step checklist every single installer has got to memorize. Step 1, switch off the AC. Step 2, switch off the DC. Step 3, verify by measurement. And Step 4, only then physically disconnect. Let's look closer at these.
Phase 1 is all about interrupting the load. First, you always hit the AC side breaker off. That stops the inverter from exporting power and stops it from pulling current from your solar string. Right after that, flip the DC switch on the inverter. Boom. Your string is now on an open circuit. The voltage is still there because of the sun, but your current has safely dropped to 0 amps.
Phase 2 is verification. Never just trust the physical position of a switch. Switches can fail. You have to grab a proper 1,000-volt DC meter and confirm there is absolutely zero load current. Check your voltage, check your polarity, verify zero current. And honestly, for ultimate peace of mind, you can literally toss a specialized tarp or opaque canvas over the panels to block the sun completely.
Only now, when you have measured 0 amps, are you cleared to physically disconnect. And when you do, please use the correct, specialized tool to unclip the MC4 connector. Squeeze those locking tabs with the tool and ease it apart. Strictly avoid yanking it by force, no jamming screwdrivers in there, and put the standard pliers away. Using the right tool prevents micro damage to the plastic that could easily cause a high-resistance fire down the road.
The massive engineering takeaway for this entire manual: a DC arc is infinitely more dangerous than a hot cable. It hits massive temperatures instantly, and it doesn't put itself out. The true hazard isn't just that the system is sitting at 600 volts. The catastrophic danger is 600 to 800 volts combined with 10 to 15 amps right as you pull a connection apart under load. So again, never, ever interrupt a live DC circuit by pulling an MC4 connector apart. Which brings us to our final slide, and a question I really want to leave you with. Knowing all this now, knowing the hidden, instantaneous devastation of a DC arc and how a tiny gap can spawn a 3,000-degree plasma fire, are your current disconnection habits actually a ticking time bomb? Take this visual manual, put these safety protocols into practice immediately, and make sure you treat DC electricity with the serious respect it demands. Thanks so much for tuning into this explainer. Stay safe out there and keep learning.